Hello everyone, in this video we are going to provide some MATLAB examples about the control engineering and specifically on the state space control and the transfer functions. First of all, we are going to start with the eigenvalues and eigenvectors of a n by n matrix. A is a square matrix and n is a dimension of the n by n matrix. And here lambda are the scalars, which are the eigenvalues, and the v's are the eigenvectors of a matrix. That the specific definition of the eigenvalues and eigenvectors are the a times v is equals to scalar lambda multiplied by v. The corresponding MATLAB function is eig of a that can provide the eigenvalue and eigenvectors. In this example, we can see that for a 2 by 2 and a b 3 by 3 matrix, the eig of the a can give us the eigenvalues of a matrix. That are 2 numbers for the a and 3 numbers for the b. For the eigenvectors, if we are going to have the eigenvectors as well as the eigenvalues, we should add them in a bracket, something like that, which is v comma d is equals to eigenvalues of the a. Here v are the eigenvectors and the d are the eigenvalues of a matrix. We should know that we have n eigenvalues and n eigenvectors correspond to each of the eigenvalues. In this example, which is the previous one, which a is 1, 2, 3, 1 and b is a 3 by 3 matrix, by just using the bracket v and d is equals to eig of a matrix, we can have the v, which are the eigenvectors of a matrix, and d, which are a square matrix that the diagonal elements are the eigenvalues of the matrix. We should actually pay attention that the eigenvectors are not the unique ones. Here in this example, we can see that how to compute the eigenvalues of the system. We should make the determinant of the lambda minus a is equals to 0, which have for these examples, the lambda are 1 and 3, and for the eigenvectors, we should construct the equation that the lambda I multiplied by v is equals to 0, that each element of the v should satisfy these equations. And the final step is that the solution of a matrix can be found as here, that beta 1 times e to the first eigenvalues multiplied by the eigenvectors, and the second one, for example, that the b2 times e to the eigenvalues multiplied by the eigenvectors. Here for these examples also a is minus 1, 1, minus 8, 5, and the eigenvalue and the eigenvectors are computed as here. As I said before, the eigenvectors are not unique and every coefficient of them can be considered as the eigenvalues that just should satisfy the eigenvectors equations. The next concept is the controllability and the observability of a matrix. Consider the system that x dot is equals to a times x plus bu and the y is c times x. In these examples, for the controllability, we should construct a controllability matrix, which is b, a, b, a to b, and end up by a minus 1, b, n is the dimension of n by n matrix, and b is n by 1 matrix, which is an input matrix. If this controllability matrix has a full rank, then our system is controllable. If it's not full rank, the system is not controllable. The corresponding MATLAB function is CTRB of a and a b matrix. Here in these examples, a is a 3 by 3, b is a 3 by 1, and the function CTRB will calculate the controllability matrix, and if this matrix has a full rank, it's controllable, and if it's not controllable, it's not full rank, it's not controllable. So for example, for a 3 by 3 matrix, our controllability matrix should be 3 by 3. Here for another example, which x stat is equals to a times x plus bu, a is 2 by 2 and the b is 2 by 1. The controllability matrix is consisting of the b and ab, which obviously shows that the rank is equals to 1, so the system should not be controllable. Again, with the same process, we can see that the MATLAB can confirm this result, that these matrices with these a and b will not be considered as a controllable systems. Here our a and b, then CTRB of the a and b, and finding the rank of these matrices, which is 1, is less than 2. The situation that the matrix is full rank, so the system is not controllable. This system can be stabilizable if the eigenvalues, which is not controllable, is stable. For these systems, for the observability, we should construct these matrices that the first row is C, the second row is CA, and ending by C by A to the n minus 1. And here again, n is the dimension of n by n square matrix of the A. So since the A is 2 by 2 and C is 1 by 2, the observability matrix should be a 2 by 2 matrix. If this observability matrix is full rank, then the system is observable. The corresponding MATLAB function is OBSV of the A and the C. Here we will see that the same process, the system can show us if it's observable or not by using the function OBSV of A matrix comma C. Here in these examples, both controllability and observability matrix can be computed. Here's for the another examples, the observability of these matrices, which obviously is not full rank, so the system is not observable, and the MATLAB should confirm this result also. For checking the observability, we need the A and C matrix. For the controllability, we need A and B. The relationship between the state of the system and the inputs are for the controllability, and the relationship between the state of the system and the output of the system are considered as observability concept. Here we can see that since the rank of the observability matrix is less than 2, so the observability matrix is not full rank and the system is not observable, but same as the previous one, can be detectable if the eigenvalues of the system that are not observable are stable. Here for the next part, we are going to go through the pole placement. Consider the system that has the x that is equals to a times x plus bu, and the system has some eigenvalues that can be computed easily. Then if the system is controllable, it means that we can put the eigenvalues of the closed loop system anywhere that we want by using a state feedback control. U is equals to minus k times x. The k can be computed as the ACKER of the A, B, and J. J are the desired eigenvalues of the system. So by having the A, B, and J, if the system is controllable at first, we can put the poles of the closed loop system at the desired values, which are defined by J. Then our corresponding k will be computed here. You can see that A, B, and J are defined by using this function ACKER will place all the poles in a predefined value. And actually there are another function which is place that can be used in the same fashion. Consider again another example that A is these 3 by 3 and B is 3 by 1 matrices, and J are a 3 by 1 matrix, which are the position of the desired poles of the closed loop system using the state feedback control. Our control is U equals to minus K times X, and the goal is to finding the K matrices. If we could find K, we can construct our control, which is equals to K times X, where the K is the gain and X is the state of the system. Here for these examples, we can see that with a different K, we can place our closed loop poles at the location that J will tell us. It's equals to minus 2, positive, negative 2 times. Here is another system that we can see A, B, and J, where A is a 3 by 3, B is 3 by 1. And after finding this K, we can implement this K to the system, then using the function SS, which is the state space of the A minus BK, I from identity from 3 by 3 matrices, and having the initial condition of 1, 0, 0. Then here we can see the behavior of the states of the system. That the first state will start with 1, and the second and the third states will start with 0, and all of them will go to 0 after, I think, 2 seconds. Which means that our control is working very well here. Here's another example. As we know, there is other way to find the K, which is equals to a row vector matrix 0, 1 multiplied by the inverse of the controllability matrix multiplied by substituting A in the characteristic equation of a matrix. Here, first of all, we are going to find the controllability matrix, which is a 2 by 2. Then using this equation, the K will be computed as 14 and 57. And here we should make sure that the desired eigenvalues are minus 5 and minus 6, which can construct the characteristic equation of the A is equals to lambda 2 plus 11 lambda plus 30. Here again, by using the controllability matrix, we will make sure that the system is controllable, and by using the ACKER for the placing the poles of the closed loop system on minus 5 and minus 6, the corresponding K gain will be computed. As another example, you can see that for these systems, x that is equals to a times x plus bu, the closed loop system is A minus BK, which can be computed as here. We are going to find the K1 and K2, which the determinant of the lambda minus the closed loop system. Place the poles of the closed loop system at a predefined value. As we can see here, the lambda minus 2 is not controllable using the K1 and K2, so this system is not controllable. And actually we can verify this result with the MATLAB, that this system is not controllable. Here with A, B, and finding the rank of the controllability matrix. And since the controllability matrix has a rank from rank 1, system is not controllable. Which can verify the result that we found by computation in the previous slide. Here is another example that the eigenvalues of the A matrix here are as lambda 1 and lambda 2, and the control is U times minus kx, and the closed loop matrix will be computed as here. And then for the characteristic equation, for having the poles of the closed loop system at minus 10 and minus 10, then the k1 and k2 will be computed. We are going to do these examples using the MATLAB. Here you can see that 2 by 2 matrix, the desired poles of the closed loop system can be found as and 145. You can see that the eigenvalues of the system has the positive values, which verifies that the system is not stable, but using this state feedback control, you can stabilize the system and put the poles on the minus 10 and minus 10. Here again, for the another example, first of all, we are going to see that the controllability matrix is full rank and its determinant is not equal to 0. So by using the state feedback control and put the desired eigenvalues at the minus 4, positive, negative 4 times I, the K gain can be computed at 31 and 7. With the MATLAB, first of all, the rank of controllability matrix is 2, so it verifies that the system is controllable. For having the eigenvalues at the predefined one, the K is equals to 31 and 7, which was computed before. Here's another example for the observability, and we are going to design an observer for having the eigenvalues of these observers at predefined one. The corresponding equation can be seen here as the L, that it will be computed as 19 and 80. We should make sure that the system is observable in this regard. Since the system is not observable, we cannot find the inverse of the observability matrix, which is needed here. And in the MATLAB, we are going to put the eigenvalues of the observer of the system on minus 10 and minus 10. After making sure that the system is observable, the related gain can be computed as the values that we computed before, 19 and 80. For the compensator, after designing the K and L, the compensator dynamics, as you know, it's equals to xc dot is equals to ac xct plus bc y of t, and the uc is equals to cc multiplied by xc of t. Here AC is A minus BK minus LC, BC is the L matrix, which is 1980, and the CC is equals to negative K. So steps is to finding first of all K, then L, then plugging them in these equations to find the compensator's dynamics. Here we can define A, B, C, then design the K and L based on the desired location of the poles, and then by the compensator dynamics equation we can find the AC, BC and the CCs. Next part, you are going to find the matrix exponential. If we have a matrix A, how can we compute the e to the AT? In this case, first of all, we are going to Start with the eigenvalues again. First of all, finding the eigenvalues of the A matrix and then finding the eigenvectors. Then we will go through the exponential of a matrix, which is e to the at, which can be calculated by the MATLAB easily. Is 2 by 2 matrix, two different eigenvalues and two eigenvectors. Here, if you have a n by n matrix, you can easily find the exponential of the matrix, as can be seen here. Here you can see that the right steps for finding the matrix exponential is to find t e to the lambda t inverse, which t is a matrix consists of the eigenvectors of a system at its column, and the t inverse is the inverse of the t. And e to the lambda t is a square matrix, diagonal one, which on each of the diagonal is e to the lambda I tv, where the lambda I are the eigenvalues of the system. Then here is the right steps to find the e to the at. If the a has n different eigenvalues of the system. Here again, it will verify that finding the exponential of the matrix can be done easily by the MATLAB. The next concept is a transfer function. If we have a system x that is equal to a times x plus bu and y is c x plus yu, if we are going to have a relationship, a transfer function that can connect the output of the system to the input of the system, the formula is c times si minus a inverse b plus d. MATLAB can easily compute this one by the function ss as the state space to transfer function tf of the a, b, c, and d. By defining the a, b, c, and d, the transfer function will be computed by the numerator and denominator of the transfer functions. It will give us the coefficient for the numerator and the denominator. Here we can see that the transfer function should be defined as 1 over 1 s squared plus 3 times s plus 2, which is the coefficient of the numerator and denominator. The corresponds MATLAB function is ss2tf. The next concept is the minimum order observers. That first of all we will define k, and then for subtracting the system and extracting the minimum order part by the ABB and AAB, and finding the K and L, and actually for defining the observer gain we should use the pole placement function in the case that we should use A transpose, C transpose, and the L or J. Here we will find the K, KE, which are the gains for the system and for the minimum realization. Here is another example to have a 4 by 4 matrix. This system can be distributed into 4 2 by 2 matrices. For each of them, the corresponding feedback gain will be computed. Here we can see that for the 4 by 4, the state feedback gain can be computed as this 1 by 4 matrix. Here's also another example. For testing the state response to the initial condition for the design minimum order observers. Here we can see that we are going to plot all the states of the system, their behavior. Here we will see that the states of the system goes to 0, starting with their initial condition. For the next one, we're going to find the transfer function for these A, B, C, and D. Also, for the situation that we have defined the K and KE, again using this S2TF to have the transfer functions. The previous examples we found the K and KE to 21.3, 3.2, and for the KE 12 and 84. You can see that the coefficients for the numerator and denominators are computed as like that. Here's for the observer design. If we design our K and KE, L, the observer controller will consist of the state of the system and the error of the system, which we are going to put the error to the 0. This 4 by 4 matrix, for example, here can be defined as A minus BK, then BK for the second element of the first row, then a 2 by 2 matrix, 0 matrix, and then the next one. Here you may find the response of the system and the states, all the states of the system. You can see that the control has been done very well. This system is a 3 by 3, one input and the one output. The transfer function will be computed for the first step using this A, B, C, and D. So here we can see that for the A, B, C, and D, the related transfer function will be computed as like that. The coefficient for the numerator and denominators, that it's almost minus 54 s minus 122 over s3 5s2 plus 36s. Now for the step 2, we are going to find the L gain, the KE, which is the placement of the subsystem of ABB, AB, and the desired minus 10 and minus 10 to find the observer gain. Here we can see that by defining K and KE. Now we are going to find the closed loop characteristic equation by multiplying these two denominators of two systems, that we can have the whole system characteristic equation. That for the first system, it's using the K that we defined in the first step, and for the second system, using the KE, and by multiplying these two denominators, the characteristic equation for the whole system will be defined as these coefficients, which is from order 5. Then again, for this system, by extracting this subsystem ABB, AAB, and the ABA, we'll compute the K of E equals to minus 1, the first row, and the 6.25 for the second row, for using the placing the closed loop system to predefined value by L. Then we are going to find the transfer function for this observer controller. As we can see here, by defining A hat, B hat, A tilde, B tilde, and C tilde for the closed loop observer controller system. The transfer function will be defined as here. Now we are going to test the response of the system using this K, KB, and KE, which were defined in the previous steps, to see what's going to happen for the states of the system. Can see them that all the states of the system goes to 0. For another example, then again finding the K and KE for the controller and for the observer dynamics, we are going to have their closed loop poles. These two equations defined by J and L, and the main system is x that is equals to a times x plus bu, and the y is equals to cx, where the a, b, and c are defined here. First of all, we are going to find the k and ke, k for the controller gain and the ke for the observer gain. For the k, we should find the pole placement of a, b, j, and for the observer one, a transpose, c transpose, and the l. Then these two gains will be computed here, k 1.3 and 0.5, and for ke 15 and 24.5. Then using these two gains and closing the loop and having the whole system, now we are going to find the response of the system to the initial conditions using this k and ke. Here we can see that the first and second states, in addition to the error dynamics, that all of them will go to 0 after almost 2 or 3 seconds. First of all, we are defining the k and ke, and for the whole system, a minus bk0, a minus kc. For the AA matrix, and the final step to finding the transfer function of this state space representation. That instead of a, we should use a minus ke multiplied by the c minus bk and ke and k, then 0. Our new a is a minus ke c minus bk, our b is ke, our c is k. Using this kind of equations, the transfer function will be computed here. Using subsystem for the minimum order observer, AAV will be 2, ABB minus 1, and LL is minus 8. Then using these three to find the KE, we will use ACTR function to find the KE, to have the observer gain is equals to minus 8. which k is equals to 2.5. Now in this stage we are going to find the response of the system using these design values. Here we are going to plot the states of the system in addition to the error dynamics. And the final stage is to finding the transfer function for this minimum order observer. The transfer function will be calculated using the function SS2TF of these new A, B, C, and D matrices. The next part of this video is for the optimal control. We'll start there. For the optimal control, our goal is to minimizing this cost function based on the states of the system, x multiplied q multiplied x, plus u or u. The integral of this function should be minimized for the system that's defined by the x that is equals to a times x plus pu, if the u is equals to minus k times x. As we know, the k will be defined as r inverse b multiplied p, and the p should satisfy the last equation. In order to define it in the MATLAB, we are going to have the a, b for the system and the q and r for the cost function. Then our goal is to find first of all p to satisfy the last equation, and then finding the gain of the system, gain of the controller. Here the corresponding function is LQR. LQR of the A, B, Q, and R will give us the K and P and E matrices. For another example, for testing the response of the system using this design K, our code subsystem A matrix will be A minus BK, identity from order 3, identity, identity. Now we are going to show what's gonna happen for the states of the system using this control that minimizes the cost function. Our method is LQR. Here's are the behavior of the states of the system. For the fast response of the previous one, instead of using Q as an identity, we can increase the speed of the system by increasing the value of the Q11 to 100 and the Q22 and Q33 to be 1. Then we are going to find the new K using the LQR function and then compare it with the previous ones. main difference between these examples and the previous one in the value of the Q11. In both of them, Q is a positive definite matrix with this new K. Our new K will be with the new Q, our new K will be changed to these values.